All right, Chapter 9 review. It's going to cover questions 54 through 83, and then I'll make a quick video to cover the last 5 questions from 84 to 88 that revolve around Chapter 10. They're actually very easy. I was looking at them again today, so we should be fine there. Number 54 says determine the first 5 terms of the sequence a sub n equals cosine of n pi over 2. All that we're asking to do is plug in a 1, a 2, a 3, a 4, and a 5 for the first 5 terms. So the first term, denoted a sub 1, would be cosine of 1 pi over 2. A sub 2 would be the next one, which would be 2 pi over 2, or pi. Then we get cosine of 3 pi over 2. Then we get cosine of 2 pi over 2, or 4 pi over 2 rather. And then we get cosine of 5 pi over 2. Normally I wouldn't simplify them right away. And in this case, because we're just listing them in an order of different terms in the sequence, I don't know if I would be so concerned about simplifying them anyway. So we're good to go in this case. But I did decide to simplify them on my own. 55. Write an expression for the nth term. So I see that each one of these has a 1 followed by a plus sign. I also noticed that the denominator of the fraction is 2 that is doubled every time. So to write 2 doubled, or rather yet, to write doubled every time, not 2 doubled, you would write 2 to the n. And just to make sure that that fits, plug in numbers for n. If I plug in a 1, I get 2. If I plug in a 2, I get 4. If I plug in a 3, I get 8, and so on. Now the numerator, there is a pattern between all of those numerators. However, they're more easily determined by what the denominator is. So it's the denominator minus 1. There's your nth term. If you had something that was equivalent to this, it would give you would get credit for that as well. 56. Determine the convergence of the following series. So at first glance, when I look at this series, I see a quadratic denominator, and it's a factorable quadratic denominator, which means that this is going to be the telescoping series. It's n plus 2 and n plus 1. And the way that we do a telescoping series is the same way we do partial fractions. We take the fraction 8 over n plus 2, n plus 1, and we turn it into 2 separate fractions with constant numerators that are 1 degree less than the denominator. 8 should be equivalent to a times n plus 1 and b times n plus 2. It's what each of those fractions is missing for that common denominator. Logically, it makes sense for me to let n equal -1 because that cancels out my a term, giving me a times 0 and b times 1. So when I solve this, it means that b is going to be the number 8. If I let n equal -2, then I get 8 equaling a times -1 plus b times 0, making a equal -8. To look at this further, I'm going to turn the page and we are going to examine what this looks like when it's actually stretched out. So I'm going to rewrite it in a different order. I'm going to put 8 over n plus 1 first. Alright, so I'm saying that this series is equivalent to the series from n equals 1 to infinity of 8 over n plus 1 minus 8 over n plus 2. I believe that's what it was. Yep. And I'm going to look at what this looks like when I start to expand it. If I plug in a 1, I get 8 over 2 minus 8 over 3. If I plug in a 2, I get 8 over 3 minus 8 over 4. If I plug in a 3, I get 8 over 4 minus 8 over 5. And it doesn't take me long before I can start to see quite a bit of a pattern. I find it helpful to make as many terms for the end as I have at the beginning. So if I had 1, 2, 3 terms in the beginning, I would do 3 at the end. And I would start with what I see. Well, these aren't very big, so I'm going to come down here. Okay, I know each one of them is going to have 2 fractions being subtracted. I know that the last term is going to be exactly what I was taking the series of in the first place. And I know that if I go backwards 1, then whatever's in the position that matches that position, it's going to be 1 less than that for n. So 1 less than n plus 1 is n. 1 less than n would be n minus 1. Do the same on this side. 1 less than that would be 8 over n plus 1, and then 1 less than that would be 8 over n. And I'm going to see what cancels. I have a negative and a positive 8/3. I have a negative and a positive 8/4. I have a negative and a positive 8 over n plus 1, and I have a negative and a positive 8 over n. I can assume that this 8 over n minus 1 is going to cancel with the right side of the previous term, and I usually note that with a dotted crossing out, because it's not really canceling with something visual, but it's implied that there will be a canceling coming up. And positionally, if that one cancels that way, so does this one. If I have 1 term in the beginning left over, I should have 1 term in the end left over. So this series is equivalent to the limit as n approaches infinity of 8 halves minus 8 over n plus 2. If n is approaching infinity, then this fraction is approaching 0, leaving 4 as my final answer. Now, what's nice about a telescoping series is not only are we proving that it's convergent because we have an answer, but we're able to figure out what the sum is. That summation means the sum. And if I'm able to cancel everything out except the beginning and the end, I know that I have a concrete sum at the final, at the end. There's very few of these series that I can figure out the sum of. Telescoping series is one of them. Geometric is another. Partial sums is the other. That's it. Nothing else can give you the sums. So don't try and do a sum formula on a P series or something like that. 57. N equals 0 to infinity of 17/3 times negative 8/9 to the n. This is a geometric series. The rule for a geometric series is to take your r value, which in this case is negative 8/9, and identify its absolute value as either being between 0 and 1 or greater than 1. This is between 0 and 1, and if that's the case, then we have a convergent geometric series. If you have a convergent geometric series, that's one of the things we can find the sum of. The sum is equivalent to a, which is 17/3, divided by 1 minus r, which is negative 8/9. Just take a moment to simplify what I see. 1 is going to be equivalent to 9/9, so this becomes 17/9. And we know that if you have fractions divided, they really become the reciprocal of the second one and multiplied. So I have a sum of 3 at the end of this geometric series. So again, telescoping and geometric are two examples of series where we can actually find the sum. That's rare. 58. We have another geometric series. It's geometric. I can identify because it's of the form a times some sort of ratio to the nth power. This ratio has an absolute value that's greater than or equal to 1. And if that's the case, then it's a divergent geometric series. Now, as I go through these, if I do it a particular way, it doesn't mean that that's the only way to do it. You may do it another way. But, for instance, if we had a geometric series and I find that it's convergent, I'm able to find the sum. But if you use a different method for it, let's say the ratio test, and you find that it's convergent, you won't know that the sum is possible because you didn't identify it as a geometric. This is divergent, so we're stuck. We're done. Scroll down, and we have another geometric series. I'm going to automatically rewrite it as 1/4. Even though I don't see 1 to the n, 1 is so versatile that I can write it that way without there being any issue. So 1/4 to the n is equivalent to 1/4, both raised to the n. So now again I have a geometric series. It's important to label what test or what series I'm looking at as I'm identifying this. The r value is between 0 and 1. Therefore, this is convergent, leading me to a sum of 9/1 minus 1/4, which is 9/3/4, which is 9/1 times 4/3, or better yet, it's equivalent to 12. So that's the end of geometric and telescoping. We move on to the integral test in P-series, 60. The series of 1/n to the pi. A P-series is 1/n raised to some sort of power on the bottom. So in this case, my P in the P-series is a p-value of pi. The exponent is pi. And the P-series test says that if your p-value is greater than 1, this is different than geometric, then it's convergent. Anything that's between 0 and 1, including 1, would be divergent. Notice I'm not going any further. This is the extent of what that problem looks like. All right. I know that this is not an integral test because if I treat one of these as u, the other one is not the du. So I am going to look at it in terms of a simplified exponent. This is n to the 1/2, and this is n, which is equivalent to the series 1/n to the 1/2. That's the rule of exponents. In this case, I have a p-series again, and my p-value is 1/2. But this p-value is between 0 and 1, including 1. Therefore, this is a divergent p-series. Because the next one is in the section of integral test, I'm going to use the integral test. But if I was in a testing situation, I would probably jump to the nth root test and be done with it really quickly. But again, just to practice the integral test, I'm going to use that. The integral test brings us back to lesson 8.8, where we take the limit. I'm going to use b here. The improper integral, 1 to b, the limit as b approaches infinity, of e to the negative x dx. This needs to be balanced if that's supposed to be e to the u, and it balances with a negative 1 on the inside and a negative 1 on the outside. The integral of e to the u is itself. So once that's balanced, I was able to integrate it very easily. Rewriting this and making it look a little bit more clean, this becomes 1 over e to the b minus 1 over e to the 1. 1 over e to the b, as b approaches infinity, is going to approach a fraction value of 0. So I have a final answer. Oh, I forgot that this is negative, sorry. So I have a final answer of positive 1 over e. Because that's positive and finite, then I can make the distinction that this, using the integral test, is a convergent series. Okay. 63. The series from 1 to infinity of the natural log of n over n. Whenever I see natural log, my instinct is to go to the integral test. So the limit as b approaches infinity from 1 to b of the natural log of x over x dx. The derivative of the natural log of x is 1 over x dx. So I know that this is u, and the 1 over x dx is my du. When I integrate that, it just becomes u squared over 2. If you want to do a u sub off to the side, you can do that, but just be careful with your bounds. In this case, I would leave bounds off, do a u sub transition, then resubstitute back in your 1 and your b and your natural log and so on. So this is natural log of b squared over 2 minus the natural log of 1 squared over 2. Natural log of 1 is 0, so this whole fraction becomes 0. And the natural log of infinity is infinity. This is positive, but it is not finite. Therefore, this is a divergent series using the integral test. All right, we move on to 9.4, which is all about comparison test. We've got the direct comparison test, and then we've got the limit comparison test. So in this case, what I do is I immediately imagine the direct comparison test, and if I can't strip down my fraction into a basic parent function, then I'm not interested in using the direct comparison. I'll go right to limit comparison. So, for instance, like I don't have a problem comparing this to the very basic parent function 1 over n squared. Remove the coefficients, remove the constants, and I want to know if I can make a bold statement as to which one of these is clearly smaller than the other. Okay? If I multiply by 3 and add 4, I have a larger denominator. And a larger denominator implies that I actually have a smaller fraction. I'm dividing by a bigger number. Now what's nice about this is that I know this to be a convergent p-series whose p-value is 2. If that's convergent, then it forces this one to be convergent, and that's what the use of the direct comparison test is. So direct comparison test, I'm making a final statement that this is convergent. Make sure in each of these, and I didn't do it up here, in each of these you're telling what test or what type of series you're identifying. 65. So 65 is one of those that I would not use the direct comparison test for, because even though I can strip it down to 1 over n cubed, I'll pause for a second while you let that settle in. Like, I would lose my coefficients and I would have n squared over n to the fifth, which reduces to 1 over n cubed, and that is a convergent p-series. I have a denominator and a numerator that are both increasing, and I don't want to compare them and run the risk of making a mistake where there might be something that's bigger. My words are all jumbled, but basically this is a little bit more complicated, so I would just stick to a limit comparison because then I don't have to think about it. I still am going to compare it to 1 over n cubed though. The limit comparison does not matter which one you put on top, but since I'm doing a fraction divided by a fraction, I am going to skip a step and I'm going to multiply by the reciprocal. Now remember, that is a convergent p-series, 1 over n cubed. I have 2n squared and n cubed together for my first term, which is 2n to the fifth. And the first term down here is 3n to the fifth. So if I use the rule that says just pay attention to the leading coefficients if the exponents match, then 2/3 would be my limit. 2/3 is finite and positive. I don't even think it needs to be positive. Maybe it does. But either way, this right here, a finite number, proves the following. It proves both. Okay? Both what? Well, when we're comparing it to something, we're comparing it to a test, or we're comparing it to a series that already has an identity. So this is going to take on the identity of the series we compared it to. And I already told you that this one came from a convergent p-series. Now it's not convergent in the way that it looks right here. That would definitely be divergent because the exponent would be -3 if I brought it back down to the bottom. But it was originally 1 over n cubed, and the p value was 3, making it convergent. Therefore, if that's convergent, then they're both convergent. (66) I'm going to compare this one to 1 over n, but remember, because this doesn't just strip away and have a single constant numerator, I am going to use the limit comparison test again. So what happens when I compare n over n squared plus 3 and 1 over n? Which again, if I'm dividing by 1 over n, I'm going to change it to a multiplication of n over 1. I get n squared over n squared, which is 1. 1 is completely acceptable for a limit comparison test. 1 is finite and positive. Therefore, I can make the distinction that both these two series, n over n squared plus 3 and 1 over n, are both what? Well, 1 over n is a divergent p-series. It's specifically referred to as the harmonic. So they're both divergent. Alright, moving on to alternating. Alternating series have a two-part criteria in order to determine whether they're convergent or divergent. If it's convergent, then you can take it a step further and determine what kind of convergence it is. So we've got -1 to the n plus 1 times n over n squared plus 1. It's a alternating series because I've got -1 raised to either n or n plus 1 or something like that, so I know that it's changing from negative to positive each instance. Criteria. If I take the limit of the non-alternating piece, this is bottom heavy. If I take the limit, is it 0? And it was. The second thing to keep in mind is if I plug in n plus 1, is my fraction going to be less? Well, sometimes this is hard to identify as we have a growing numerator and a growing denominator. So what I encourage people to do in this case is type into y1, the first one here, and then type in the second one. And then look at the table. Okay, if we're trying to prove that the left side is less than, the left side is less than the right side, is that true for all the numbers from 1 on? Is 2/5 less than 1/2? And it is. Is 3/10 less than 2/5? Well, if I converted this, it would be 4/10. So therefore, that would be a larger fraction on the right. Okay, if I wanted a common denominator here, multiply everything by 10, I'd get 40 over 170. Multiply everything by 17 over here, and I would get 51 over 170. And that's a larger fraction on the right. And that's going to consistently be the case. So this is a larger fraction on the right. All right, so if I know that these are telling me that I have a convergent series, then I can take it a step further and say, okay, well, what if it was the non-alternating series right from the beginning? What can you tell me about n over n squared plus 1? And actually, we have the proof, basically similar proof right up here for question 66. It's going to be done the same way. I'm going to use a limit comparison test with the stripped down parent function 1 over n. I already know that 1 over n is a divergent p-series. If I take the limit, and I do need to show my work, of n over n squared plus 1 times n over 1, I am going to get 1. Finite and positive means that these are both divergent. So if I have a divergent after I've already established convergence, then this is what we call conditionally convergent. It's convergent, but only for a certain time. -8. -1 to the n factorial over 1 times 3 times 5 times ... times 2n minus 1. Alright, first thing I'm going to ask myself is the limit equal to 0? Well, n factorial is n times n minus 1 times n minus 2 times 6 times 5, well, times ... 6, 5, 4, 3, 2, 1. Now I stretched that out because I want you to see what's actually happening here. So 2n plus 1, if we're going odd numbers, then I'm going 2 less than that. This is what the odd numbers would look like. They wouldn't be decreasing by 1, they'd be decreasing by 2 because I'd have to jump over the even number to get there. Now I see that 1, 3, and 5 cancel. And what conclusion can you draw from what you're noticing here? Well, I'm seeing every other number canceling, but look at what's not canceling. So the odd numbers here would be every other one. It might cancel these two, it might cancel that one, I'm not sure. But either way, I'd be left with an n type on top and a 2n type on the bottom. Okay? Let me look at this in a different way. Let's pretend that we were looking at specifically n equals 5. What would the term n equals 5 look like? You would have 5, 4, 3, 2, 1 on top. And then you would have 1, 3, 5. And if I plugged in 5 here, I'd get 10 minus 1, which would be 9. So I'd have to go up to 9. Okay? How would you describe this fraction? And I'm hoping that as you look a little, look at it for a little bit, you'd realize that this is bottom heavy. That's going to be the case as you go on. If you wanted to graph this, I don't know how far out we'd have to go for us to see that this is, in fact, that it has a limit equal to 0. But if I wanted to take x and then do factorial over, well, again, this would be hard to do because I can't do dot, dot, dot here. So just trust me when I say that it is going to be decreasing and the limit is going to be 0. Now, if I plug in the next one, is that equal to the previous, or is it less than the previous? Right? I'm not going to take this to 2n. I have to go one more than that because I have to jump 2 spaces. Here's what I would do. I want you to imagine dividing both of these fractions or simplifying both of these fractions by what they have in common. They all have everything from 1, 3, 5 up to 2n minus 1 in common. So I'm going to get rid of those. This fraction has n plus 1 times n factorial. And this fraction has the n factorial. Cancel those. So now, is n plus 1 over 2n plus 1 less than 1? Well, the limit of this is going to be 1/2, and that is in fact less than 1. So again, when I'm canceling these things, I'm talking about limits. So this is again going to be convergent based on those two criteria. Good news is I won't give you one like this on the test. I think this is a little bit more challenging than need be. All right, so then the non-alternating piece. If I look at this, I'm going to use the ratio test for this. N plus 1 factorial over 1, 3, 5, 2n minus 1 times the reciprocal of the original. This is going to look very familiar to what we just did. Note that is going to cancel with all of that. All of these are going to cancel with all of these. And I'm left with the limit as n approaches infinity of n plus 1 over 2n plus 1. The limit is 1/2. If I throw two convergents together, then I can make the statement that this alternating series is absolutely convergent. Okay? Nice break from that is the ratio and the root test. They are very, very nice. Now, it's not out of order, but it kind of is. The alternating piece oftentimes will require something like a ratio test after that. So even though ratio test came in the curriculum afterwards, I did use it, but that's okay. 69, and we have n equals 0 to infinity of n factorial squared over 3n quantity factorial. Anytime I see factorial, my gut tells me to use the ratio test. It's the n plus 1 term times the reciprocal of the original. And this is going to require quite a bit of stretching out, so give me a moment. This becomes n plus 1 factorial times n plus 1 factorial. This becomes 3n factorial. This becomes 3n plus 3 factorial, and n factorial, n factorial. This is n plus 1 times n factorial, n plus 1 times n factorial, 3n factorial, over 3n plus 3, 3n plus 2, 3n plus 1, 3n factorial, n factorial, n factorial. Whew. Those cancel with those. The 3n factorial cancels with the 3n factorial. And I have n plus 1 in the numerator, but 3m plus 3, 3m plus 2, and 3m plus 1 in the denominator. That's a 27n cubed in the denominator and an n squared in the numerator. This is equivalent to 0, which is less than 1. And according to the ratio test, that's a convergent series. Moving on, we have the series from 0 to infinity of -1n, -1 to the n, 2 to the 4n over 2n plus 1 factorial. Again, my gut would tell me to use the ratio test because I see a factorial in there. Factorial says take the next one, the n plus 1, plugged in for every n that you see. Times the reciprocal of the original. Take a moment to stretch out what I have. This is 2 to the 4n plus 4, so it's 2 to the 4n times 2 to the 4. This is going to be 2n plus 2 plus 1, so it's 2n plus 3 factorial. And I stretch my factorial until I see that it is a repeat of the other factorial that I see in the numerator, so that I can cancel those. I can cancel the 2 to the 4n's. I can cancel the -1 to the n's. I know that the absolute value of -1 is irrelevant. And I get 16 in my numerator over multiple n's in the denominator. Here's another example of 0, which is less than 1, therefore this is a convergent convergent series using the ratio test. Okay. In 71, it's slightly different. I do see a power of n, but because not everything has the power of n, I'm not going to use the nth root test. I reserve that for when I have a power of n attached to the entire question. So I'm going to use the ratio test again, which is the n plus 1th term over the original. 3 halves n to the n plus 1 and 3 halves to the n just differ by 1/3 halves. And their limit as n approaches infinity of n plus 1 over n is 1. This comes out to 3 halves. That unfortunately is greater than 1, which according to the ratio test is a divergent series. If it was equal to 1, then we would use, or we would say that it was inconclusive. 72. Here's an example of where the entire operation is raised to the power of n, so I would do the root test. The root test has the same criteria values as the ratio test, but the approach is to take the nth root of what you see. The nth root of something to the nth power is just what's inside. And the ratio of the coefficients here, because the limit, because we have n values raised to the same power, the limit is going to be 2. 2 is greater, I guess I should put x values around it, but greater than 1, and just like in the ratio test, that means that it is divergent. '73, I think we did one very similar to that. I don't know if it was necessary to put here. I would use the ratio test here because not everything's raised to the power of n. So n plus 1 to the e negative n plus 1 over 2, or times e, and n e to the negative n over 2. Take a moment to clean this up because negative exponents are very telling. E to the negative n over 2 is e to the n over 2 in the numerator, and e to the negative n plus 1 over 2 would be e to the n plus 1 over 2 in the denominator. And this is the same as saying n plus 1 times e to the n over 2 over n times e to the n over 2 times e to the 1/2. Right? If I distribute this over 2, it would be n over 2 and 1 over 2. These cancel. These have a limit of 1. My final answer is 1 over e to the 1/2. That's going to be less than 1. Therefore, this is a convergent series based on the ratio test. Okay, moving on to 9-7, or 9-7. We're kind of doing a little bit of a change of direction here. Question 74. Maclaurin. If you have a Maclaurin polynomial, then you know your C value is 0. We're doing the 4th degree, which means that I have to write this down and do 4 derivatives of it. The first derivative would be the derivative of the first. I'm going to try and do this the way that you guys learned. 1 e to the x plus x e to the x. The second derivative would be e to the x plus 1 e to the x, x e to the x, which simplifies to 2 e to the x plus x e to the x. The third derivative would be 2 e to the x plus 1 e to the x plus x e to the x, comes up to be 3 e to the x plus x e to the x. And the fourth derivative is 3 e to the x plus 1 e to the x plus x e to the x, which is 4 e to the x plus x e to the x. So this portion right here is the product rule, and it's found in each of these when I take the derivative of that portion of it. Okay. Evaluate each of these for 0. If I plug in 0, I get 0 in the beginning. If I plug in 0 for the first derivative, I get e to the 0, which is 1, and 0 for the other portion. If I plug in 0 for the second derivative, I get 2 times e to the 0, which is 2, plus 0. Third derivative, it's going to be 3. And the fourth derivative is going to be 4. So the fourth Maclaurin polynomial takes each of these numbers as the coefficients, has x minus 0 because it's Maclaurin, and the pattern is 0 for the exponent, 0 for the radical, or for the factorial in the denominator. 1 times x minus 0 to the 1 over 1 factorial. 2 times x minus 0 squared over 2 factorial. 3 times x minus 0 cubed over 3 factorial. And finally 4 times x minus 0 to the 4th over 4 factorial. Clean this up. This has a 0 coefficient, so it goes away. That's a 1, that's a 2, that's a 6, that's a 24. This simplifies to 1x over 1, which is just x. This simplifies, well, the 2's cancel, to x squared. This simplifies to x cubed over 2. And then the last term simplifies to x to the 4th over 6. Number 75 is a Taylor polynomial whose center point is pi. But luckily we're only doing 2 derivatives here. So the first derivative would be 2x cosine x plus x squared times negative sine x. Or better yet, let's write this cleanly. And then its derivative would be 2 cosine x plus 2x times negative sine x. That's the first portion. Now the second portion would be negative 2x sine x. Derivative of sine is cosine, so negative x squared cosine x. Let's see if I can clean this up a little bit. These become negative 4x cosine, or negative 4x sine x. Alright, evaluate all of them for pi. If I plug in pi, I get pi squared, and the cosine of pi is negative 1. This becomes 2 pi cosine, which would be negative 1, minus pi squared. Sine of pi is 0. And then second derivative, 2 times negative 1 minus 4 pi times 0 minus pi squared times negative 1, which simplifies to negative 2 plus pi squared. So my third degree Taylor polynomial starts with negative pi squared x minus pi to the 0 over 0 factorial plus negative 2 pi x minus pi to the 1 over 1 factorial plus the quantity negative 2 plus pi squared times x minus pi squared over 2 factorial. I'm not doing anything to simplify that further because I don't see it being very helpful. Granted, you can get rid of the 0 pi here and the 1 pi, or the 1 factorial and the 0 factorial. You can do that if you want, but I'm just going to leave it alone. Well, Moving on to 9.8. Question number 76 says, find the interval of convergence. You've got a couple options. You can either use the ratio test if you're more comfortable with that, or you can use the geometric series if you're more comfortable with that. Technically, this is written as a geometric series, so I can just bound this between -1 and +1, but I'm going to pretend that I didn't know that, and I'm going to go right to ratio test, because ratio test works every time with this. This gives me 2x. According to the ratio test, it's got to be bound between -1 and 1. So my interval is -1 to, or -1/2 to 1/2. But the problem with the ratio test versus the geometric series is that I need to check the endpoints. So I'm going to do this out loud so you can see that this is still going to be divergent, like it would be if it was the geometric series. But you should plug them in. So if I plug -1/2 in for x, I get -1 to the n. That would be -1 plus 1 plus -1 plus 1, or 1 minus 1, and so on. And that is definitely divergent. If I plug in 1/2, I get 1 raised to the n power, which is 1 plus 1 plus 1 plus 1. So clearly that's going to be going on forever. So that is also divergent. Your final interval of convergence is -1/2 to 1/2. It is centered at 0, and you can say that your ratio of, or your radius of convergence is 1/2 from 0. 77 is definitely not a geometric series, so I would have to go about this with the ratio test. Take the limit as n approaches infinity. -1 to the n plus 1, x to the n plus 1 over n plus 2.
You are currently the only person in this conference.
And then n plus 1 over -1 to the n, x to the n. That cancels with that. This cancels with that. And these have a limit of 1. I still have a -x in the top. The negative is irrelevant, so I'm looking at this as the absolute value of x. If I bound it between -1 and 1, there's my interval, but I need to check my endpoints. So what would happen if I plugged in -1? What kind of series would I be looking at? Well, -1 times -1 is a +1, so when I squeeze those together, it's +1 to the n over n plus 1, or rather just 1 over n plus 1. This, according to a direct comparison test with 1 over n, larger denominator, smaller fraction, and that's a divergent, larger denominator. Okay, I can't do that because that's divergent. So if I do limit comparison test with it, 1 over n plus 1 times n over 1, get a limit of 1, which means that they are both divergent. Okay, so if that's divergent, then this is going to stay less than. Plug in 1, and I now have an alternating series. The limit of 1 over n plus 1 is equal to 0. 1 over n plus 2 is a smaller fraction than 1 over n plus 1. So according to these, it's convergent, which changes this interval, or which changes that symbol to an equal sign as well. Okay, we're getting close, 78. ratio test. We've got x minus 2 to the n plus 2 over n plus 2 to the 4n plus 2 times n plus 1, 4 to the n plus 1, x minus 2 to the n plus 1. These differ by 1, these differ by 1, and the limit of those is equal to 1, leaving x minus 2 over 4. So if you bound that less than 1, then that means that we are stuck between negative 1 and 1. Multiply each of those by 4, add 2, and we need to check our endpoints. If I plug in negative 2, I get negative 4 to the n plus 1 over n plus 1 to the 4, or times 4 to the n plus 1. This is really the alternating series, negative 1 to the n plus 1 times 4 to the n plus 1 all over n plus 1 times 4 to the n plus 1. We already did an alternating series of 1 over n plus 1 in the previous example, I believe. Its limit is 0, and it is decreasing, so I know that that's going to be convergent. Skipping a few steps here. If I plug in 6, I get 4 to the n plus 1 over n plus 1 times 4 to the n plus 1. Now I'm looking at the series 1 over n plus 1, which if I use the limit comparison test with 1 over n, I'm going to find out they are both divergent. So that's the new interval, negative 2 to 6, including the negative 2. Note 79. I'm just going to jump to the limit. I've got the limit as n approaches infinity of 2n, 2 times n plus 1, quantity factorial, x over 2 to the n plus 1, L over 2n quantity factorial, x over 2 to the n. I'm going to get rid of that right now. My numerator becomes 2n plus 2, 2n plus 1 times 2n factorial. This is infinity. Infinity is much greater than 1. Therefore, this would normally be divergent, but it's not absolutely divergent. It is convergent somewhere. So we would say that this is convergent only at c equals, well, where is this centered? There's nothing being subtracted from the x, so it's centered at 0. And we can also say that that means that our radius of convergence is 0. We're going nowhere in our convergence. (9.9) representation of power series. We've got f of x equaling 3 over 2x minus 1, and we are going to center that at 0, which means that I don't have to subtract anything from my x value. It's important to have the x value written second. It's also important to have this symbol in the middle being a subtraction problem. So if I multiply everything by a -1, I do have the minus that I need. It's also important to have this first term be a 1, and it is, so I don't have to go any further. This is the geometric series from 0 to infinity of -3. That's my a value. I throw my r value in here, and this is my geometric series. Now, in order to identify its interval, take the r value and look at its absolute value in comparison to 1. That means that it's stuck between -1 and 1. Divide everything by 2, and I get -1/2 and 1 being my endpoints. Geometric series, if I plug in -1/2 or +1/2, I get 1 in here. I don't want 1. 1 is going to give me a divergent geometric series. So I don't have to check my endpoints. They just are -1 to, well, -1/2 to 1/2 non-inclusive. All right, 81. I've got a power series of 1 over 2x minus 5 centered at -3. First thing I'm going to do is write it in the correct order. Second thing I like to do is center it. It's +3. Now be careful. I just added 3, but because there's a coefficient here of 2, I technically have increased my denominator by 6. So now I have to balance it with a -6. That -6 belongs in the front with the -5. I need that middle symbol to be minus. And I need this first term to be 1. My power series goes from 0 to infinity. -1/11 is my a value. The 2x plus 3 over 11 is my r value, raised to the n. You could simplify that numerator as 2x plus 6 if you wanted to make it look a little easier. And then the geometric series says that that 2 times x plus 3 over 11's absolute value is less than 1, which means it's stuck between -1 and +1. Multiply everything by 11. That's the order you have to do this. There is an order. Some people have been doing things like dividing by 2 right away, or you have to be careful not to go and do all of that stuff. It's got to be done in the correct order. In this case, because it's 2 times the entire set, I can do divided by 2. But if it was 2x plus 3 and there weren't parentheses, do not divide by 2. If you want to use decimals, you can, because they're nice decimals. 3 subtracted from all 3 sides. Well, 3 is equivalent to 6 halves. So this would be -17 halves. And this would be 5 halves. And again, I do not have to check my endpoints. Last section of chapter 9. Question 82, and it says, determine the Maclaurin series for f of x equaling e to the 3x. Because it doesn't identify an n value, then we need to go as many derivatives out until we see a good solid pattern that we can predict. The derivative of this is going to be 3e to the 3x. Its derivative is going to be 9e to the 3x. Its derivative is going to be 27e to the 3x, and I think at this point you're seeing that everything is just going to be multiplied by 3 every time, if you didn't identify that already. Maclaurin means that I'm going to be plugging in 0. And if I plug 0 into the exponent of e, it just turns e to that number into 1. So this is going to be 1, 3, 9, and 27. That gives me a Maclaurin polynomial of 1 times x minus 0 to the 0 over 0 factorial, 3 times x minus 0 to the 1 over 1 factorial, 9 times x minus 0 to the 2 over 2 factorial, 27 x minus 0 to the 3 over 3 factorial, and so on. Our job is to now put that in a series formation. Each of these coefficients, 1, 3, 9, 27, are 3 to the n if I start at 0. Right? 3 to the 0 is 1. 3 to the 1 is 3. 3 to the 2 is 9. They all have x minus 0, so I can just simplify that to x if I want. Since I'm starting at 0 and these are going to both be 0, I can write n and n factorial going toward infinity. This is my answer. You could also put the 3 and the x together since they share an exponent and write it as 3x to the n over n factorial. Both of those would be appropriate. And 83, we have a Taylor series of sine x, and we're going to center this at pi over 4. Oops. Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of negative sine is negative cosine. And if I go one more, then I repeat my cycle from the beginning. If I evaluate my original at pi over 4, I get root 2 over 2. If I evaluate my derivative at pi over 4, I get root 2 over 2. If I evaluate my second derivative of pi over 4, I get negative root 2 over 2. Third derivative, I get negative root 2 over 2. Fourth derivative, oops, that's messy. I get root 2 over 2. Alright. Root 2 over 2 times x minus pi over 4 to the 0 over 0 factorial. Root 2 over 2 times x minus pi over 4, 1 factorial. Negative root 2 over 2, x minus pi over 4 squared over 2 factorial. Negative root 2 over 2, x minus pi over 4 cubed over 3 factorial. And then root 2 over 2, x minus pi over 4, the fourth over 4 factorial, dot, dot, dot. This one's a little bit more difficult, a little bit more challenging because the exponent, this is not an alternating series. It's not every other one that's changing. It's in groups of 2. So there is an answer to this. I'm going to give you that, but we're going to fill in the rest of the blanks. We know for sure that there's a root 2 over 2 portion to this. We also know that there's a negative 1 to some power. We also know that x minus pi over 4 exists every time, and it's n over n factorial. That negative 1, and of course I don't think I have my homeworks with me, but I am going to go back to 9.10 because I'm pretty sure that they established what that looks like. Hopefully you're being patient with me. I remember. There's a question from the homework, and I used an odd number near it to answer it. Okay. So number 4, number 3. So in section 910, question number 3's homework. Open up to 910, number 3. has negative 1 to the n times n plus 1 over 2. And I'm going to double check that that works. If it doesn't, then I'm going to change that around to make sure that it works for us. So if I plug in 0, I get 0 times 1, which is 0. That would mean that the first term would be positive. If I plug in 1, I get 1 times 2. The 2 and the 2 will cancel, and the next term would be negative. So that won't work for us. What if I change this to an n minus 1? It's all trial and error. If I plug in 0, I still get 0, which is going to be a positive 1. If I plug in 1, I get 1 times 0, which becomes 0, another positive. If I plug in 2, the 2 and this 2 will cancel. That will be raised to a 1, giving me a negative. If I plug in 3, I get 3 and 2, the 2's cancel, I get another negative in a row. If I plug in 4, the 4 and the 2 will cancel to a 2, giving me a positive. Okay, so that does work. So let me clean this up a little bit. Root 2 over 2 is multiplied by all of them. I'm just going to bring it out front to get it out of the way. Negative 1 to the n times n minus 1 over 2, x minus pi over 4 to the n, all over n factorial. Okay, and that is all of chapter 9.